Hello friends, so today we are going to solve the questions from the year 2019. There are total 10 questions and all these 10 questions are from the mains. The first question, it states that 4-point charges minus q plus q plus q and minus q are placed on y-axis at y is equal to minus 2d, y minus d plus t and plus 2d respectively. The magnitude of electric field E at a point on x-axis at x is equal to capital D with capital D is much larger than small d will behave as. So we have to find out the proportionality relationship between the capital D and the electric field. And all these charges are on y-axis. So we can just draw an approximate figure for that. So this is our x-axis and y-axis, our origin, and we have charges plus q and minus q at plus d and plus 2d. So let us suppose this is our plus d and this is our plus 2d. Similarly, we are going to have minus t and minus 2d. And the charges are given to us at plus 2d we have negative, at plus t we are having positive, and similarly minus t positive and minus 2d is negative. Magnitude is same for all the charges. We are, let us suppose a point P is there whose distance from the origin is given as capital D, and okay, so here we are given electric field we need to find out at point P, and so we can say that electric field direction wise, suppose the first charge, so it's electric field, and this will be other one, this will be same because the charge is our minus q here as well as and minus q here also. Okay, and suppose this is our electric field 1 because of this, and we are going to have electric field 1 because of the charge which is at minus 2d. Then we are having other two charges. One charge is at plus t and other charge is as minus t, and their magnitude is same, that is plus q as well as plus q. Therefore the electric field because of these will be same but opposite to that of our this even. So we can say, let us call this electric field as our E2. Similarly, we can call this electric field also as E2. And the angle made by E1 is, let us suppose, theta 1. On the other side it is theta 2. Sorry, the angle will be same, it is theta 1. And because of this E2, let us suppose the angle is given as theta 2. Other E2 will be also giving us angle of theta 2. Now we can easily divide this E1 into respective components. So let me draw this point separately. So this is a point and we have a axis. First electric field is our E1 making an angle of theta 1. So we can divide this into two components. This will be our E1 cos of theta 1, and on the y-axis we are going to get our E1 sine of theta 1. Similarly, we can divide other E1 on the along x-axis. It will be same, so we are going to get this as E1 cos of theta 1, and because of the other E1, this will be also E1 cos of theta 1, so we can write this as twice E1 cos of theta 1. And on the y-axis it will be in downward direction, that will be our E1 sine of theta 1, and these two are going to balance out each other. So for E1, the only electric field that is present is toward positive x-axis. Now we come to the E2, and this is our E2 making the angle of theta 2. We can divide into two components. One component will be our along negative x-axis opposite, so this will be E2 cos of theta 2, and the other component will be along positive y-axis, that will be over E2 sine of theta 2. Next is our other E2. So one component will be along negative y-axis, that is our E2 sine of theta 2, and the second component will be same, that it is in this direction, so we can directly write it as E2 because the angle is same and the magnitude, that is E2 is same, so we get twice E2 cos of theta 2. And here also this E2 sine of theta 2 and E2 sine of theta 2, they are direction opposite, so they are going to balance out each other. Therefore the net electric field will be only in because of the cosine component, but in minus y direction, and the other cosine component, in minus x direction, another one in plus y direction. Therefore we can write the net electric field. So for point P, suppose this is point P, in that direction we are having 2E1 cos of theta 1, and on the opposite direction we are having twice E2 cos of theta 2. So net electric field at P, net electric field at point P, let us call that as EP, okay. And we can write that this EP will be equal to twice E1 cos of theta 1 minus twice E2 cos of theta 2. Cos of theta 2. And we can easily find out our cosine function of theta 1 and theta 2, because this is our nothing but a right angle triangle. So therefore we can say our cos of theta 1 will be equal to distance d, and distance between the origin and the point is d, so this comes as d square plus small d square, square root. Similarly we can write cos of theta 2 is equal to our d upon d square, and the distance is twice t and whole square and its square root. Okay, 1 second, I think this theta 2 is d. Okay, this has to be theta 2 and this has to be theta 1. Okay, because theta 1 is because of 2d. Yeah, so this distance is 2d. Yes, so this looks good now. And so we can just substitute them, and we get our EP will be equal to, this comes as E1 will be equal to our twice KQ divided by d square plus E1, one second, E1 is because of, this is our theta 1, let me check it again. To E1 is this, so this comes as one second, there is some one second, and the distance so we can find out the distances, that the charge at minus d2, we are going to get this distance will be equal to 2d, and this is our, yes, so this comes as, one second, So we are going to get this as 2kq and d square plus d square multiplied by capital D, and this comes as d square plus capital D square and square root minus, so this will be 2kq divided by, this will be our 4 theta 1 and theta 2, and comes as d square plus this will be 2d whole square multiplied by capital D, and d square plus d square plus 2d square and its square root, and we are only interested in the denominator, okay, and numerator we can take common, so we get this as 2kq capital D, and here you get 1 upon d square plus capital D square 3 by 2 minus, and this also come 1 upon 4 d square plus capital D square and 3 by 2, and we are given that our capital D is very large than small d, therefore we can say that we can just ignore our small d, so we get this as this will be equal to 2kq capital D, and we can take this common and raise to it in the numerator, so this comes as 1 minus d square 3 by 2 minus 3 by 2 rather, and this comes minus, and this comes as 1 plus, this is plus 1 plus will be equal to our 4d square capital D square, and this is minus 3 by 2, and here it comes as d cube. Okay. Therefore now if we expand using the binomial, this comes as 2kq d upon d cube, this will be your 1 minus 3d square divided by 2d square, and this will be minus our 1 minus, and this will be our 12 upon 2 d square upon capital D square, and if you open the bracket, this 1 and 1 goes away and this comes as plus, so we get from here that our 2kqd d cube, this will be equal to minus 3d square, and this will be our 6, and this will be coming as 12d 9, so this comes as 9 by 2, so this will be 12 upon 2, and we have this as d square, capital D square minus 3d square upon capital D square, and this is our 2. So from here we get this will be coming as 9, 9 goes by 2, so this is left with 2kqd upon d cube multiply by d square upon capital D square, and this d square goes with d square, d cube and d cube, so we can say that electric field at point P is proportional to 1 upon d4. Okay, so this comes as option D is the correct one. Option D is correct. Next question. It was also asked in the 2019 mains, and it states that 2 point charges minus q1, that is square root of 10 microcoulomb, and q2 minus 25 microcoulomb are placed on the x-axis at x equal 1 meter and x equal 4 meter respectively. The electric field at a point y is equal to 3 meter on y-axis is. So here we can just draw an approximate figure for that, and so this is x-axis and y-axis. Point on x-axis is given as at 3 meter. So let us suppose this is our 0, 3, and here we have to plot 2 points. One is at x equal 1. So let us suppose this is at x equal 1, and this other point x equal to 4. And the charges are point 1 is given as q1 and q2 is our negative. So we can just find out electric field because of this q1. Let us suppose that is our E1 and its direction will be our E1, and the second electric is because of our q2 and its direction will be towards the charge, that is our E2. Let us suppose their angle are theta 1 and theta 2. And this is our suppose point P. So at point P we can just, you can say, divide the respective electric fields into their respective components. So this is our point P. We are having E1 in this direction, and this is a horizontal line. So we are going to get this angle will be our theta 1. Therefore we can write that one of its component will be our E1 cos of theta 1 and the other component will be its E1 sine of theta 1. And the second field is our E2, and that is something like this. This is our E2. So this angle will be our theta 2. So we can say this component will be our E2 cos of theta 2 and the other component will be our E2 sine of theta 2. So we found out the components that are associated with our electric field. Okay. And their respective distances are also given to us. So this distance is our 3, this distance is our 1, and this distance will be our 4. Therefore, we can say that their magnitude of the electric field, the general formula for electric field, that is our E, is equal to 1 upon 4 pi epsilon naught, and this is our charge divided by square of the radius. So this is the general formula for the electric field. So we can just find out the value of our E1. So we can say our E1 will be equal to our 1.4 pi epsilon naught. It comes as 9 into 10 to the power 9, and the charge is suppose our Q1, and Q1 is given to us as square root of 10 into 10 to the power minus 6, and the distance will be this will be our R1 and this will be our R2. So R1 will be 3 square plus 1 square. R1 will be our 3 square plus 1 square and its square root. So we can write this will be equal to our 3, 3, 9, 10. So therefore, and it whole square. Okay, so we get this as that electric field E1 will be coming equal to as 9 into 10 to the power 9, and this comes as 10 minus 7, so it comes as square root of 10 to the power minus 7. Therefore, we can write that our E1 will be equal to 9 square root of 10 and multiply by 10 raised to the power 2. So this is our E1. Now we can write this in the vector form according to the components, because we have two components, one in the sine, other one is in the cos. Therefore, we can say that our E1 will be equal to, we just found out magnitude, that will be common factor 9 square root of 10, and this is 10 raised to the power 2, and we have cos of theta 1 that is in minus I direction. This is our minus I. Cos of theta 2 is our, E1 is in plus j. So we get this as cos of theta 1, and we have this as minus of I plus sine of theta 1, and this is our plus of j. And we can easily find out our theta 1, that our tangent of theta 1 is equal to 3. Tan of theta 1 is equal to 3. So we can find out our cos of theta 1. We get cos of theta 1 is equal to 1 upon square root of 10, and sine of theta 1 will be equal to 3 upon square root of 10. So this gives us that our E1 will be equal to 9 into square root of 10 raised to the power 2, and we can write this as minus 1 upon square root of 10 I unit vector plus 3 square root of 10, and this comes as j unit vector. And here this 10, 10 and 10 cancels out. Therefore, we get our E1 in the will be coming as 9 into 10 raised to the power 2, and this comes as minus of I plus 3 of J. So this is our first electric field. Similarly, we can find out our E2. So we can say our E2, its magnitude will be equal to 1 upon 4 pi epsilon naught is 9 into 10 raised to the power 9, and the charge is our E2. E2 is our minus of 25. So we get this as 25 into 10 raised to the power minus 6, and the distance will be our 4 square, and this comes as 3 square, and square root its whole square. So this will be our 25, and so E2 will be coming as our 25 and goes with 25, so we are left with only 9 and 10 raised to the power 3 volts per meter. And similarly, we can write it in the form of our cosine and sine function. That is our E2 vector magnitude is our 9 into 10 raised to the power 3, and our E2 is our plus I, and this is our minus J. So we can write this as cos of theta 2I, and this comes as plus sine of theta 2 and minus of J. And we can easily find out our cos of theta 2 as well as sine of theta 2. Cos of theta 2 will be equal to 4 by 5, and sine of theta 2 will be equal to 3 upon 5. So we substitute the value, we get our E2 will be equal to 9 into 10 raised to the power 3, and this cos comes as 4 by 5 I minus this is our 3 by 5 J. And this will be coming as 4I and 9 into, okay, we are going to make this factor as same, because here we are having 9 into 10 raised to the power 2, and this is 9 raised to the power 10 raised to the power 3. So we are going to just modify it. So we can write this as 9 into 10 raised to the power 2 and multiply inside 10. So this comes by 40 by 5, and this comes as 45ij minus 30 by 5j, which we can write as E2 will be equal to 9 into 10 raised to the power 2, and this goes by 8, and this goes by 6. So we're left with 8I minus 6j. So we have our E2 as well as we have our E1. So we can easily find out the electric field. That is our E will be equal to our E1 plus E2. We substitute the values and we can take this factor as 9 into 10 raised to the power 2 as common, and E1 was our minus I plus 3j, minus I plus 3j, and here it is plus I minus 6j. Therefore, we get this as 9 into 10 raised to the power 2, and this comes as 8i, and minus I is 7i, and this comes as minus 3j. And we can just now multiply by 9, and this comes as 63i minus 27j, and multiply 10 raised to the power 2 volts per meter. So this comes as 63 and minus 27, so option A is correct. Option A is correct. Next question. It says that three charges plus Q, Q and plus Q are placed respectively at a distance of 0, d by 2 and d from the origin on x-axis. If the net force experienced by plus Q placed at x equal to 0 is 0, then the value of small q is. Okay, so we have three charges, plus Q, small q and plus capital Q, and they are placed respectively at a distance. So we can just draw an approximate figure, and suppose we are having, this is our origin, this is our d by 2, and this is our d. At the origin we are having a charge that is plus capital Q, d by 2 is small q, and our d is also our plus q. And it says that the net force on this particular charge is 0, is equal to 0. Under this condition we have to find out the value of small q. So we know the general formula of the force. We can say that force F is equal to K Q1 Q2 upon R square. So let us find out the force acting on the charge at the origin, because this distance will be our d by 2 and this distance will be our d. Okay, so let us first of all find out the force because of this charge, which is at d. So you can say force on charge plus q at x is equal to 0, and there will be two forces. First it will be due to plus q at x is equal to d. Okay, so these are both positive, so it will be a repulsive force. Okay, so we can say, let us call this as our F1. So F1 will be equal to K, and this comes as our Q square upon D square, and its direction will be towards left. Next is our force due to Q at x is equal to d by 2, and this force will be depending upon what will be the sign of this q. Okay. So it means if our this q is greater than 0, then the direction is important, because it says that net force is 0. So in this case the direction will be towards left, because both are positive. So direction on q will be towards left, repulsive force. And then we have q that is less than 0. So therefore the direction, and please remember this is direction of force on capital Q. Okay. On capital Q, when q is less than 0, that is mean negative, the force will be towards right, which will be attractive. Okay. So it says that net force is equal to 0. Net force is given to 0, therefore our q will be a negative charge, and the direction of the force on q will be right. Under this condition only there will be net force is equal to 0. So therefore we can say that our F2 will be equal to our K, and this comes as Q. We can just interested in magnitude, and it comes as d by 2 and whole square. And this will be our K Q, and this comes as our d square multiplied by 4, and the direction towards will be our right. So net force is 0. Therefore we can write that this is our F1, and here this K will be a common factor on both, so we can just equate it directly, and we get this as Q square upon d square is equal to Q modulus of Q divided by d square multiplied by 4. D square and square goes with Q, therefore we get that our capital Q is equal to 4 times modulus of Q, and we need to find out this small q. So we can say from here this small q is equal to capital Q by 4, and this charge has to be negative, so this will be coming as negative. Okay. So the option is our D is the correct option. Option D is correct. Next question. It says that in a free space, a particle A of charge 1 microcoulomb is held fixed at point P. Another particle B of the same charge and mass 4 micro kg is kept at a distance of 1 millimeter from P. If B is released, then its velocity at a distance of 9 millimeter from P is. So we are given that we have two charges A and B, and both are having same mass as well as charge. Okay, so we can just draw an approximate figure for that. We are given that we are having a charge A. Let us suppose this is our charge A, and it is held at a fixed point P. So this is our fixed point P, and B is is kept at 1 millimeter. Suppose this is our charge B and the distance between them is our 1 millimeter. As they are having same charge, obviously they are going to repel each other, and this charge B will try to move along towards the right. And it says that as soon as B is released, its velocity at a distance of 9 millimeter from P. Suppose it reaches this point, that is a B prime, and its distance of this B prime from A is our 9 millimeter. So we are going to find out the velocity at this particular point. So let us see that initial distance is our R1 and the final distance is our R2. And here we are going to use conservation of energy principle. Initial energy is equal to final energy. So you can say conservation of energy which gives us that initial total energy is equal to final total energy. And so initial total energy is, initially this charge is at rest, so kinetic energy will be 0, and it is going to have only the potential energy, or we can say electrostatic potential energy. So we can say this as U of I plus K of I is equal to U of F plus K of F. U of I is our K Q square upon R1 square plus 0 is equal to final energy is our K Q square upon R2 square plus this comes as half mv square. And please remember, this conservation of energy is with respect to charge B. Okay. So from here we can write that our half mv square will be equal to kq square, we can take as common, and one second, energy is not r square but is r. So this comes as 1 upon r1 minus 1 upon r2. We are supposed to find out the energy, velocity rather. So we can say our velocity square is equal to, this comes as 2k q square divided by mass m, 1 upon r1 minus 1 upon r2. We know all the values, so we substitute them. We get this as v square will be equal to 2, value of k is 9 into 10 to the power 9, and charge is given as same, that is our 1 microcoulomb. So this comes as 1 into 10 to the power minus 6 whole square, and mass is given as 4 microcoulomb. So this comes 4 micro kg, 10 to the power minus 6, and our R1 is our in millimeter. So this comes as 1 into 10 to the power minus 3 minus 1 upon 9 into 10 to the power minus 3. Now this is our all calculations. So we can write our v square will be equal to, this will be coming as 4 into 10 to the power 6. So v will be equal to square root of 4 into 10 to the power 6, which gives that the velocity will be equal to 2 into 10 to the power 3 meter per seconds. So we get option number D is the correct one. Option D is correct. Next question. It states that a system of 3 charges are placed as shown in the figure. If capital D is very much larger than small d, the potential energy of the system is best given by. The basic figure is given to us. We are given 3 charges, plus Q, minus Q and capital Q, and the distance between the plus Q and minus Q is d, small d rather, and distance from the midpoint of this plus Q and minus Q to the charge Q is given as capital D. So this question we can solve by using 2 approaches. One is more a traditional way. We can consider that initially only charge Q is present. From infinity we brought a charge minus Q at a distance of d, find out its energy, and then we brought this Q in the presence of both the charges plus Q and minus Q, and the respective distances will be our, because this distance will be coming as d minus small d, and this distance will be coming as d plus small d. Okay, and then we add all these energies, we can get the potential energy of the system. Second approach is, if you look closely, these 2 charges constitute a dipole. Okay, so we independently know the potential energy of dipole, and independently we can find out what will be the energy associated with this capital Q in the presence of the dipole system. That is much shorter approach, okay, because we know both the formulas. Therefore, we can say that potential energy of the dipole, let us call this as U1, will be equal to our K. General formula is Q1 Q2 divided by D, which comes as minus, because one charge is positive, another one is negative, and it will be coming as Q square, and distance between them is our D. Then we can easily find out the potential energy of capital Q in the presence of dipole system. So potential energy of Q in the presence of dipole, we can call this as U2. U2 will be equal to, this is our minus K, and we have this as charge capital Q, small q, and distance between them is our center is capital D square, and multiply by D, that's the distance between the dipole. Now we can just add them and get the total energy. You can say our total energy, that is suppose that is a U will be equal to U1 plus U2. So U1 we know is our minus K Q square upon D, and this comes as minus U2 is our K Q D square multiply by D. And there is no need to solve it because answer is given directly in the standard format, because as such there is, so we are just put the value of K, which is minus 1 upon 4 pi epsilon naught, and this comes as Q square upon D, and this will be our plus q small q d square multiplied by small d. This is our total energy. So the option is our minus of this, and okay, minus is not taken common, so let me write it. So this is not taken as common, so this will be minus as well as this is minus. So we have our option number D is the correct one. Option D is correct. Next question. It says that a positive point charge is released from rest at a distance r0 from a positive line charge with a uniform density. The speed v of the point charge as a function of instantaneous distance r from the line charge is proportional to. So basic figure is given to us. We have a line whose charge density is given as plus lambda, and we have a point charge that is also our positive. Obviously there will be a repulsion between them, so this point charge will be moving towards our right side. So initial distance will be r0, and our final distance, let us suppose somewhere here, it is our r. We need to find out the speed. Okay, so we can just find out electric field, and then electric field we can find out our, you can say, potential difference, that will be our energy, that will be giving us energy, and conservation of energy will be resulting in us a velocity equation. So we can say that our electric field due to a infinite line charge and that electric field distance, that is our r function dependent upon r, will be equal to lambda upon 2 pi epsilon naught and divided by r. Okay, and it will be, and we are having 2 points. One is at distance of r0 and another is at a distance of r. So based on this we can easily find out their you can say the potential difference based on the electric field. So we can say that potential difference between the points, and let us put this point as A and this point as B. So we call that potential difference between 2 points. And we can write the equation that our V of r minus V of our r0 will be equal to minus, and this comes as our r0 to r integration, and this is our E of r prime multiplied by our D of r prime. Okay. Here we are taken another variable r prime just to differentiate it with respect to r. That's the only function, otherwise it doesn't matter. So we can just substitute value of our, this comes as r0 and r, and E of r prime is our lambda upon 2 pi epsilon naught, and this comes as r prime and dr prime. So we get this as will be equal to minus lambda upon 2 pi epsilon naught, and this will be integration of dr prime upon r prime, which will be coming as natural log of r prime. Upper limit is our r, lower limit is our r naught. Therefore, we can say potential at r will be equal to, this will be our V R naught minus lambda upon 2 pi epsilon naught natural log of r upon r naught. So we can find out the change in potential energy. Change in potential energy, let us call that delta of U will be equal to charge, that is our Q, and voltage at R minus voltage at R naught, which we already know. So we get this as delta of U will be equal to minus, this comes as lambda times Q upon 2 pi epsilon naught natural log of R upon R naught. Now we can use conservation of energy. Conservation of energy. So we can say energy at A will be equal to total energy at B. Okay. We can see initial energy. You can see our initial energy, U initial will be equal to U final. And initial energy is only potential energy because the kinetic energy is our 0. So we get this as initial energy at our R naught will be equal to final, it will be having a velocity factor, kinetic energy plus final energy at R. So we can just write it that our half mv square will be equal to our U of R naught minus U of R, which is our minus delta of U, which we just found out is our minus minus becomes plus. So this comes as lambda Q upon 2 pi epsilon naught natural log of R upon R naught. So this gives us the velocity equation. Here 2 goes with 2. So we get our V will be equal to lambda Q, this is m pi epsilon naught natural log of R upon R naught and its square root. So this is our velocity equation which was supposed, okay, relationship. So this comes as our R upon R naught, proportionality relationship. So from here we get V is proportional to natural log of R upon R naught and its square root. So option D is correct. Yeah, option D is correct. Option D is correct. Next question. It says that the electric field in a region is given by E AX plus B I iota, where E is in Newton per Coulomb and X in meters. The value of constant A is 20 SI unit and B is 10 SI unit. If the potential at X is equal to 1 is V1 and at X equal to minus 5 is V2, then V1 minus V2 is. So we have to find out V1 minus V2, and the direction of electric field is given to us. So we are given that electric field in the vector notation is our AX plus B, and this is I unit vector, obviously in the plus X direction. And we have to find out our potential at V1 minus V2. So we have to find out this V1, which is potential at X is equal to 1, minus V2, which is potential at X is equal to minus 5. This we have to find out. We know already the relationship between the electric field and the potential, that is the derivative of the potential. So we know that our electric field is equal to minus dV upon dx. So we can say electric field, we know already, formula is given to us. We can say our dV upon dx will be equal to minus of ax plus b, and and this is our I unit vector. We can consider later on if required. Okay. So from here we need to find out V1 minus V2. So we can say V1 at x is equal to 1 minus V2 at x is equal to minus 5 will be equal to, this will be our minus, and the limit of integration will be our minus 5 to 1, and this comes as ax plus b. A and b are given to us as constant, that is our 20 and 10. So we get this as minus, this comes as minus of 5 to 1, and we get this as 20x plus 10 times dx. Now we can just simply integrate them. We get this as 20x square divided by 2, that is 10x square. So we have this as 10x square, and this will be coming as plus 10x. Limit of integration will be our minus 5 to 1, minus sign. 10 we can take as common, so we get this as minus of 10. Upper limit is 1, so this comes as 10 plus 10, that is our 20. So this we get 10 common, so this is 1 square minus of minus 5 whole square, and this is our plus 1 minus of minus 5. Okay, so we get this as minus of 10, and that will be equal to our 1 and this plus 25, and plus, so this will be 24, and this will be our 5 plus 1 6, and this comes as 60. One second. Minus. Okay, because this will be minus of 25. So this comes to us as 18 minus of 10 minus of 18, giving us plus 180. Okay, so we get plus 180. Option C is correct. Option C is correct. Next question. It states that 3 charges Q plus Q and plus Q are placed at the vertices of a right angle isosceles triangle as shown below. the net electrostatic energy of the configuration is 0, the value of capital Q is. So we are given that it is an isosceles triangle. So let us assume that this distance is over A. So obviously this will be also over A, and this distance will be our square root of 2 times A, Pythagoras theorem. Okay. So we net electrostatic energy. So let us call this as plus Q is, let us put this here, point A, this is B, and this is our point C. So we can find out of energy. So energy between A and B. So we can say that electrostatic energy between, so this is between B and A. Let us call this as UBA, and that will be with K. Charges are same. This is Q and Q. Distance is our A. So this comes as K Q square upon A. Next is energy between B and C. B and C, let us call this a UBC, which will be our K. Charge is our Q and capital Q, distance is our A. And finally, we can find out between C and A. Let us call that a UAC, which will be equal to our K. Charges are Q, capital Q, and distance is square root of 2 times A. We are given that the net electrostatic energy is equal to 0. So we can say that summation UBA plus UBC plus UAC will be equal to 0. And we substitute their respective formulas. K will be our constant part, and KQ we can take common. So in the first we get Q upon A, plus second we get capital Q upon A, plus we get this as capital Q upon square root of 2A is equal to 0. And we can also take A as common, and this comes as divided by A. So we get from here that our Q plus capital Q 1 plus 1 upon square root of 2 is equal to 0. Therefore, we need to find out value of capital Q. So we get our capital Q will be equal to minus, and square root of 2 we can take as LCM. So this comes as square root of 2 multiplied by Q and square root of 2 plus 1. So we have this option number D is the correct option. Option D is correct. Next question. It states that 4 equal point charges capital Q each are placed in xy plane at 0, 2, 4, 2, 4, minus 2 and 0, minus 2. The work required to put a fifth charge capital Q at the origin of the coordinate system will be. So here we have to find out the energy work required to put the fifth charge at the origin. Okay, and remember all these charges are given. They are not at the origin but at a x and y coordinate system. So we can just draw an approximate figure. And charges are given as 0, 2, and we have 0, -2. Then we are having 4, -2, and we are having 4, 2. So this will be giving us something like a square. And we have to find out the work done to bring a charge at the origin at this point. So first of all, we are going to find out the potential because of all the charges at the origin. Okay. And for that, we are going to require the distances. So this distance, and let us call this as R1. So this R1 will be equal to about 2. This is our R2. So this will be also 2. Let us put this is our R3, which will be coming as this. We have 4, 4 and 2 is 4, 16, 4 square root of 20. And similarly, we are going to have this as our R4, which will be also a square root of 20. And first of all, we are going to find out the potential at the origin. Okay. So we say electric potential at origin due to each charge. Electric potential at the origin due to each charge. General formula we already know, that is our V is equal to our K Q upon R. So it will be nothing but algebraic sum. So we can say that potential at the origin, K and Q will be a common factor, so we can take that outside. That will be equal to 1 upon R1 plus 1 upon R2 plus 1 upon R3 and plus 1 upon R4. So we get this as KQ, and we have 1 upon R1 is 2 plus 1 upon 2 plus 1 upon square root of 20 plus we have this as square root of 20. So we can write this will be equal to our KQ, and this becomes a 1. So this will be 1, and this comes as 2 square root of 20. We can just solve it. KQ square root of 20 is our 2 square root of 5. So this comes 1 upon 1 plus 1 upon square root of 5. So this is the potential at the origin. Now we can find out the work done. Work done to bring charge Q to the origin. That is, suppose that W will be equal to Q multiplied by the potential at the origin. So we get work done, that is our Q, and potential is our KQ, 1 plus 1 upon square root of 5, which gives us KQ square 1 plus 1 upon square root of 5. Okay, so we need to value of K is our becomes as q square upon 4 pi epsilon naught and 1 plus square root of 5. So this is our work done, and we get this as q square square root of this. Option D is the correct one. Option D is correct. Next question. It states that a charge Q is distributed over 3 concentric spherical shell of radii A, B and C, where A is smallest, B is the medium one and C is the largest radii, such that their surface charge densities are equal to one another. The total potential at a point at a distance r from their common center, where r is less than A, would be. Okay. So we have 3 concentric spherical shells. So we can just draw the approximate figure for that. So this is innermost, having a radius of A. Then we have another circle whose radius, concentric shell whose radius is over small b, and then we have our final one which is having a C. So this is our A, B and C, and we need to find out the potential at a point at a distance r, and this r is less than A. So it means this point should be somewhere here. So let us, this is point P and this distance is at a distance of r. We have to find out the point P, and we are given that their surface charge densities are equal. So we are given that, or we know the general formula for surface charge density. Surface charge density, that we have a sigma, is equal to charge upon 4 pi r square, and we can just divide this into, you can say, or from here we can find out the charge, because charge is what we require. So we can say our Q will be equal to 4 pi r square multiplied by sigma. Therefore, for A, B and C, we can just write it that charge on A will be equal to our 4 pi A square multiplied by sigma. Charge on B will be equal to 4 pi B square multiplied by sigma, and charge on C will be equal to 4 pi C square multiplied by sigma. Therefore, we can say total charge. Total charge, let us suppose that is our capital Q, will be equal to our QA plus QB plus QC, and taking the common factors, that is our 4 pi and sigma. So we get this as capital Q is equal to, we have this as 4 pi sigma, and it will be coming as A square plus B square plus C square. Therefore, we can say our charge density in terms of the total charge Q will be equal to 4 pi A square plus B square plus C square. Now the point is inside all the shells. Okay. So we know that potential at a point inside all the shells potential at a point inside all the shells. And for the condition where r is less than capital R, okay, and this will be our same as on its surface, which is our same as on its surface. Therefore, we can write the formula that the potential inside will be equal to 1 upon 4 pi epsilon naught q upon capital R. Therefore, the total potential due to 3 shells, because we have 3 shells and this point P is inside all the 3 shells. So you can say that total potential at point R, which is less than A, due to all 3 shells. That is equal to V of R will be equal to K, and we have this as Q1 upon A plus Q2 upon B plus Q3 upon C. Basically means potential due to 1, 2 and 3, potential due to A, B and C. And Q1, Q2 and Q3 we already know. So we substitute, we get this as K, and Q1 is our sigma. This comes as 4 pi A square upon A plus sigma 4 pi B square upon B plus sigma 4 pi C square upon C. And K we already know is our 1 upon 4 pi epsilon naught. Let me write it here. 1 upon 4 pi epsilon naught. So this 4 pi cancels out throughout, and this square goes with square. So we are left with will be equal to sigma, we taken common, sigma upon epsilon naught will be equal to A plus B plus C. Sigma we just found out, we substitute its value, we get this as our Q, and sigma is our Q upon 4 pi. So this comes as 4 pi epsilon naught, and this is our A plus B plus C divided by A square plus B square plus C square. So this is the potential at the innermost point. So this comes as option number B is the correct one. Option B is correct. So this complete all the 10 questions, and all 10 questions were from 2019 mains, completing all the 10 questions. So this is part 1 of the because there are 20 many questions, so this is our part 1. Okay, the remaining question we are going to try to cover in part 2. If required, we are also going to do part 3 or part 4 for this 2019 mains as well as advanced questions later on. This complete all the 10 questions for the part 1 year 2019, and this were only for the mains. Thank you.